In this video, I'm going to be talking about problems that involve springs and use Hooke's law. So our first problem, after hanging a 2.5 kilogram mass vertically from a spring, the spring stretches 4 centimeters. And we're asked to find the spring constant of the spring and then to find the mass needed to stretch this same spring by 8.2 centimeters. So the first thing I'm going to do is draw a picture just so I know what's going on. And then after I draw a picture, I'm going to draw a free body diagram. So this is going to be the free body diagram of my mass. And so this spring has been displaced downward, so this mass is stretching the spring downward. So it's going to have a force that opposes that tries to restore it back to its original length. So the spring force is going to fight that displacement or go upward. And then the mass has a weight that is going down toward the earth. So that's it for my free body diagram, no forces acting in X. So I'm just going to start by writing what I know. So my mass is 2.5 kilograms. And my delta L, my change in length, in this case is a change in the Y direction. And it is 4 centimeters or 0.04 meters. So the reason I write it like this is because Hooke's law, or the force of a spring, is given by K delta L. Sometimes it might be written as K minus Kx, but in this case it's just K times the displacement of the spring, and then we just have to put in the direction by hand. So in this case I just looked at the picture and knew, since the spring was stretched downward, that it's going to be positive in the positive Y direction. Okay, and then if our spring was horizontal, delta L would correspond to delta X. Okay, so now that I have this, I'm ready to do Newton's law and sum up the forces. So if I sum the forces in the Y direction, I have the spring force that's going up, and I have the weight that's going down. And if I set that equal to mass times acceleration, I get 0, because once the spring has stretched, it will stop moving, and so our acceleration will be 0. Then I can substitute in for my spring force. So F spring is just K delta L, or delta Y in this case. And then the weight is given by mg, and that's all equal to 0. So now I can solve by K by moving mg over, by adding, and then I'll divide by my Y displacement. If I plug these numbers in, I get 2.5 kilograms times 9.8 meters per second squared, all over 0.04 meters. And if you plug that in, you should get 612.5 newtons per meter. Okay, so now that we have the spring constant, we can use our new displacement in part B and just solve for the mass. So we're going to do the exact same thing, and we're going to end up with the same equation, because we'll have the exact same free body diagram, but now in part B, so this is part A, part B, we'll get back to this same equation, K delta Y minus mg equals 0, but this time we know K, we have a different delta Y, and we're going to solve for m. So if I do that, I'll move this over and then divide by g on both sides. That's delta Y over g. And if we plug that in, we have our 612.5 Newton per meter spring constant that we just found. We have a new displacement, so this is going to be 0.082 meters when you convert that from centimeters. And we divide by g, or 9.8 meters per second squared, and that should give us 5.125 kilograms. Okay, so you could round that to 5.13. Okay, and so that's the mass we need to stretch this same spring by 8.2 centimeters. So in this next problem, we have a 5 kilogram block that is connected to a horizontal spring that has a spring constant of 300 newtons per meter and is compressed by 8 centimeters. And we're asked to find the initial acceleration of the block once it is released if the coefficient of kinetic friction is 0.26. So I'm going to draw a picture. We have a block connected to a compressed horizontal spring, and it's on a rough surface since there's friction. So this compression has been displaced to the left since it's being squeezed, and so that means our spring force is going to be to the right. And so if I draw a free body diagram with all my forces, this block has a weight going straight down, has a normal force from the floor pushing it up, and then the spring force to the right. Once it starts moving to the right, it will have a force of kinetic friction that is to the left. Okay, and so then if I write everything I know the mass of the block is 5 kilograms. It's been stretched 8 centimeters or 0.08 meters, and our spring constant is 300 newtons per meter. Okay, so now, just like all force problems, I'm going to start by doing Newton's laws and summing up all the forces. So I'm going to start with the forces in the y direction. I know I'm going to need the normal force anytime there's friction present, and that's typically found doing forces in the y direction. So if I do that, I have a normal force and weight. So the normal force is positive, the weight is negative, so I'm going to get negative. It's in the minus y direction, and I'll set that equal to MAY. Okay, so this block isn't going to accelerate up off the floor in the positive y direction or through the floor in the negative direction. So the acceleration is going to be 0, and all of this is going to equal to 0. And this just tells me that the normal force is going to equal the weight when I move it over, or the normal force is equal to mg. Okay, now that I know everything about the y direction, I can move to the x direction. And if I sum up the forces in x, now I have the spring force and minus friction. So I have the spring force pushing me to the right. I have kinetic friction pointing to the left once I start moving, and that's going to equal the mass times the acceleration initially. Okay. And then if I plug in, this is going to be k delta x for my spring force minus mu k times the normal force for friction, and this is going to equal mass times acceleration. And then I found the normal force in the previous step, so now I can substitute that in. So I get k delta x minus mu k mg equals max. And then all that's left is to solve for the acceleration. So all I need to do is divide both sides by the mass, and I get k delta x minus mu k mg all over the mass. And if we plug all of that in, 300 newtons per meter times 0.08 meter displacement minus 0.26 coefficient of friction, 5 kilogram mass, our value for g, and then the mass again, 5 kilograms, we get an initial acceleration of 2.25 meters per second squared. And it is important to notice this does say initial acceleration. Our spring force is going to change as the displacement changes. So once we release the mass, this spring is going to stretch again. It's going to go back to its original length. And so when delta x decreases, the spring force decreases. And so since this is not a constant force, it means our acceleration is not going to be constant. And so we're only finding the acceleration the moment after it starts to move when the spring is still stretched 8 centimeters. Once it starts to, or once it's compressed 8 centimeters, once it starts to stretch back out, this acceleration is going to change. Okay, so that's important to remember physically. So in the last problem, we have a spring with a spring constant K of 250 newtons per meter, and it is used to pull a 10 kilogram block across a smooth surface. We want to find the stretch in the spring if the block is to accelerate at 0.75 meters per second squared, and then we want to find how much the spring will stretch if it's pulled at an angle 40 degrees above the horizontal. So in this case, we want to sum the forces in the x direction. So we're going to have a spring force, and that's going to be the only force that we have, and that's going to be equal to max. So in this case, if you look at the block, the spring is being stretched, and in order for the spring to try to go back to its original length, it's going to try to pull the block in closer so that it can kind of compress itself. So that's how we know that the spring force is constant. And it kind of makes sense. If we're pulling on the spring and the box is going to accelerate to the right with us, the spring must be pulling on the box to the right. So now if we use Hooke's law to replace our spring force equals K delta L. In this case, I'm going to write as K delta X. Since it's being stretched in the x direction, set that equal to max. And then to find how much it's compressed, we just solve for delta x, which is going to be mass times acceleration over the spring constant. And if we plug in, we have our 10 kilogram block times 0.75 meters per second squared, all over the 250 Newton per meter spring constant. And we get that it will stretch 0.03 meters, or 3 centimeters. So now we can do the exact same thing for part B, except now our spring's up at an angle, and so this means that our spring force is going to have both an x and a y component. So if we want the x component, call this F spring x, we need to do cosine. So this is going to be adjacent to our angle, and we know adjacent is always cosine. So if I sum up the forces in x, now I have the x component of the spring force, or F spring times cosine of theta. And I guess you could put in 40 degrees at this point if you wanted. And that's still our only force in the x direction, so that's going to equal to mass times acceleration. And so again, I'm going to plug in my K delta X for my spring force. So I get K delta X times my cosine of 40 degrees. It's going to equal mass times acceleration. And now I can solve for delta X again. So this time I'll have to divide by K times cosine of 40 degrees. So K cosine of 40. So we're going to get the same thing, 10 kilograms, 0.75 meters per second squared over 250 newtons per meter, and cosine of 40 degrees. And if we plug that in, now it's going to stretch 0.4 meters or 4 centimeters. And this kind of makes sense. Since some of our force is going in the y direction, we need to pull even harder to get the same amount of force in the x direction as if we were pulling only in the x direction. So the spring's going to have to stretch a little bit more in order to apply that added force. In this next problem, we have two identical 5 kilogram blocks that are hung by 3 identical springs shown in the figure. And we want to find how much each spring is compressed if each spring has a spring constant of 200 newtons per meter. So I'm going to start by labeling these blocks. And then I want to draw a free body diagram for both of them. So for block A, it has a weight that is straight down. And this spring the spring has been stretched. So it's been stretched this way, so it's going to pull up on the block. So it'll be a spring force up. Okay. And then for block B, it also has a weight, and it's also attached to this spring, except this time the spring has been stretched this way. So this is kind of non-intuitive, but if you imagine just looking at the center of the spring, it's kind of being pulled in both directions. Okay, so the part that's attached to A, in order for this spring to go back to equilibrium, it's trying to pull A and B closer to each other. So the force on A is to pull it up, but on B it's trying to pull B closer to A or down toward it. So there is a spring force that is down toward A. Okay, and I'm just going to leave this as F spring since they're all identical. And then we have two identical spring forces that are up, so I'm just going to call that 2 times F spring up. Okay, so both of these have been stretched, and in order to go back to their equilibrium position, they're going to try to pull block B upward. Okay, so this bottom spring is trying to pull A up and B down, and then the top two springs are trying to pull B closer to the ceiling where they're attached. Okay, so if that takes a little bit, go back through that and make sure that makes sense and you get the directions right. And so now I'm going to start with block A, and I'm going to start summing up my forces. In this case, we're only working in the Y direction, and block A only has 2 forces, so it's the easiest to start with. So we have a spring force that is positive or straight up, and we have the weight of block A. Actually, I'm just going to put the weight since they're identical 5 kilogram blocks. And we'll set that equal to the mass times acceleration, except once we put these blocks on the springs, they're going to stretch, and then they're eventually going to stop. So they're not accelerating anymore. So this is just going to sum to 0. Then I'm going to plug in my expression for F spring and the weight. So this is Y, or K delta Y for block A. And the weight is just mg. So this just means K delta Y for block A is equal to mg. And if I solve for delta Y, or the stretch in this bottom spring, I get mg over K, or 5 kilograms times 9.8 meters per second squared, all over 200 newtons per meter. And that gives me a stretch of 0.245 meters, or 24.5 centimeters. Okay, so now I'll sum up the forces for block B. If we sum up these forces in the Y direction, we get 2 times the springs above minus the weight of the block. It's the same for both, so I'll just leave this as W. And then we have another spring force from the bottom spring, and this equals the mass times acceleration in the Y direction, but again, they're not going to move, so this is just 0. And we might want to differentiate this spring force from these two, because we don't know necessarily that they're going to be the exact same at this point. But we already know this bottom spring force. Up here we found that this spring force on the bottom is equal to the weight of one of the blocks, or the spring force minus the weight equals 0, so these must be equal. So we could just replace this with the weight of one of the blocks. So then we would get the 2 spring forces that are on top. These should be identical since they are identical springs. They're attached the exact same way, so we expect them to stretch the same amount. And here we have 2 copies of the weight, since this is just equal to the weight of one of the blocks. And so we can set that equal to 0. Okay, now obviously our 2's are going to cancel. We're going to get 2 spring forces on the left minus or equal to twice the weight. So our 2's are going to cancel. And now we get that K delta L, or the spring force, is just equal to mg. And this is what we got before. So instead of delta L, I guess I should write delta Y. And this is for the springs above B. But delta YB is just mg over K. And since the mass of the 2 blocks are identical and the spring constants are also identical, these springs are also going to stretch 0.245 meters or 24.5 centimeters. Okay.